Now let's take a look at the Newmark family of integration methods. So I'll say Newmark's integration scheme. Before going into that, again, let's take a look at the finite difference method, the forward difference method. So that's t, that's f of t, and we have a curve like this. We said that that's Tn, that's Tn plus 1. We have 2 points, this distance is delta t, and we draw a line from t to t, f of t to f of t plus 1. And we were using this slope only, right? So this is delta f and that's delta t, and we were using the slope of this curve at Tn, and we were writing the following relationship: f prime of Tn is equal to f Tn plus 1 minus f Tn, or I can rewrite divided by delta t, sorry, and I can rewrite that equation as follows: delta t is equal to f Tn plus 1 minus f Tn. So this equation, remember that this is delta f, this equation relates f prime of Tn with delta f only, okay? So in case of Newmark's integration method, I will draw the same figure. Again, that's Tn plus 1. So what we are doing is we are using this slope, whatever it is, and we are getting this value, and that's equal to f prime of Tn delta t, and here we are using this slope, and that will be equal to f prime of Tn plus 1 delta t, okay? So he introduces an additional variable, gamma is utilized to indicate what percentage of f prime Tn plus 1 enters into relationship with f tn plus 1. Okay. So he has written the following equation: fn plus 1 is equal to, instead of showing tn plus 1, I just say n plus 1, equal to fn plus 1 minus gamma f prime n multiplied by delta t plus gamma f prime n plus 1 delta t. Okay, so that's, call it equation star. So if we compare these two equations, this one and that one, so fn plus 1 will be equal to f prime n multiplied by delta t. So the forward difference is equivalent to this expression when gamma is equal to 0. So if we assign a value that's different than 0, then we use some part of this equation to obtain what fn plus 1 is. So that's the generalized form of that equation. Now, if we use equation star to relate velocities with accelerations, we have the following relationship: u dot n plus 1 is equal to the velocity at the current time step plus 1 minus gamma u double dot n delta t plus gamma u double dot n plus 1. So that's our first integration equation for Newmark's method. Now, in order to relate, so we have a displacement velocity, acceleration velocity relationship. Now I need to relate displacement with velocities and accelerations. Okay, so in order to do that, I'll say let u is equal to u0 plus u dot t plus 1 over 2 u double dot t square. You will remember this equation. This is the equation of, or the displacement velocity and acceleration relationship if you have a constant acceleration. I can write that equation in discrete form and in the following manner: un plus 1 is equal to un plus u dot n multiplied by delta t plus 1 over 2 u double dot beta multiplied by delta t squared. Let's call it equation plus, and here in this equation where u double dot beta is defined as follows: 1 minus 2 times beta u double dot n plus 2 times beta u double dot n plus 1. So in this equation, let's see what u double dot beta means. So this is time acceleration graph, and let's assume that we have a variation of acceleration as follows. So this is the nth time step, and this is the Tn plus 1 time step. So here I have u double dot n, and here I have u double dot n plus 1. So with this equation, we are still using a constant acceleration between the time steps, but we are averaging the accelerations at Tn plus 1 and at Tn. What is the weight of the Tn plus 1? The acceleration at Tn plus 1 depends on your beta value. So again, we have a still constant acceleration, but the magnitude of the acceleration, how do we do the averaging between the acceleration at Tn and Tn plus 1, depends on this beta coefficient. So let's call this one equation plus plus, and inserting equation plus plus into equation plus, we have our second integration equation in Newmark methods. Un plus 1 is equal to un plus u dot n multiplied by delta t plus 1 over 2 minus beta u double dot n multiplied by delta t squared plus beta u double dot n plus 1 delta t squared, and that's the second equation of the Newmark integration. So this one is our first equation that relates the accelerations, or that gives us the velocity at the next time step, and this is the second equation that gives us the displacement at the next time step. Now remember that our equation of motion is as follows: m times u double dot plus c times u plus k times u p times n. So at discrete time intervals, we write the equation of motion as follows: m times u double dot n plus 1 plus c times u dot n plus 1 plus k times u n plus 1 should be equal to p and n plus 1. So what we do is, instead of u double dot n plus 1, we don't do anything. U dot n plus 1, we just insert this equation into this one, and for un plus 1 we insert this equation right here, and we obtain an equation that gives us the u double dot n plus 1 for the upcoming time step. Now we usually use two types of this Newmark integration method. One of them is called the explicit Newmark integration. So in that case we will use beta as equal to 0 and gamma as equal to 1 over 2. And in that case un plus 1 will be equal to un plus u dot n delta t plus 1 over 2 u double dot n delta t squared. And the velocity at the next time step is equal to u dot n plus 1 over 2 u double dot n delta t plus 1 over 2 u double dot n plus 1 delta t. So if I call this one as my equation double star and this one as plus, so inserting plus into double star, I have the following relationship: u double dot n plus 1 in parentheses m plus delta t over 2 multiplied by c is equal to p n plus 1 minus c times u dot n plus k times un plus k times u dot n times delta t minus delta t over 2 times c times u double dot n plus delta t square over 2 k times u double dot n. And if you examine it, we can call this as our m hat, and this will give us, everything is known on the right hand side, so this will give a new force vector. Let's call it p hat at n plus 1. So my equation of motion, or the discrete version of the equation of motion, will have the following case. I have m hat multiplied by the acceleration at the next time step should be equal to the applied force. And at every time step, if you assume that m and c doesn't change, this is all known and this is all known. So that's why we call it an explicit Newmark integration method. Now let's take a look at the implicit Newmark integration. So for this case we use beta as equal to 1 over 4 and gamma as equal to 1 over 2. So if I put these beta and gamma values in equations 1 and 2, I obtain the displacement as un plus 1 is equal to un plus u dot n delta t plus 1 over 4 u double dot n delta t squared plus 1 over 4 u double dot n plus 1 delta t squared. And the velocity u dot n plus 1 is equal to u dot n plus 1 over 2 u double dot n delta t plus 1 over 2 u double dot n plus 1 delta t. And in that case, the equation of motion so the acceleration u double dot n plus 1 is equal to, so not equal to, multiplied by m plus delta t over 2 c plus delta t squared over 4 k is equal to p n plus 1 minus c times u dot n plus k times un plus delta t k times u dot n minus delta t over 2 c times u double dot n plus delta t square over 4 k times u double dot n. And that's the equation. Now if you take a look at this part of the equation, now for a nonlinear case you don't know what your k for the next time step is. So that's why you have to perform an iterative solution, an equilibrium iteration, to figure out the displacement and the corresponding k for that displacement. So that's why we call it an implicit Newmark integration. So in case of a nonlinear system, or yes, system k at t n plus 1 is not known, thus an iterative solution in addition to time integration is required. So these are the most used two Newmark methods. One of them is the explicit Newmark and the other one is implicit Newmark. Now let's take a look at the implementation of the Newmark integration algorithms. Now we'll start with the implicit Newmark method, and remember that we derive the following equation. So this part, since we are solving it for a linear case, this part is calculated in here. That's like a new mass matrix, has the contribution of C and K, and this part will be the new force vector that changes with respect to time. So at this point I'm just calculating that, okay, and the coefficients F1 and F2 coefficients are as follows. Now in the integration we go from 0 to t max, so I'm just looping over it. So at every time step I'm calculating the force for the upcoming time step, f1 times the acceleration of the current time step, f2 times the velocity of the current time step. So I'm just, these are the velocity dependent values, acceleration dependent values, and k times u. So at the initial step, they are all defined as an input, and I'm calculating the force vector for the current time step, and by dividing the force vector with the new mass matrix or the mass, I'm calculating the acceleration for the next time step, for the I+1 time step. And we have the equations for, once we determine what the acceleration is, we can determine the velocity for the next time step and the displacement for the next time step, and this is what I'm doing. So basically you repeat the same procedure over and over, and to calculate the displacements, velocities, and accelerations at every time step. That's the implicit integration. Now we also discussed the explicit integration, and in the explicit integration, as you can remember, this part in the m hat matrix, we don't have the stiffness matrix, so I don't have any stiffness dependent coefficients here, and this part is the new load vector, and I have these following written in here. This one is here. So the procedure is the same, the only difference is the coefficients. Again, I'm calculating the acceleration of the I+1 time step, and once I determine the acceleration, I can determine the velocity by using this equation, it's right here, and determine the displacement, it's right here. And again, you repeat this procedure for every time step, and you determine u, v, and a for every time step. So now let's take a look at the results. Again, I'm solving a very simple example, a single degree of freedom system. So let's show it this way. I'm just solving it for a free vibration. So k is equal to 20,000, and mass is defined as 400, and I'm applying a harmonic force P that's equal to P0 times sine omega t. I have the damping defined here, but for this example problem, I will consider the damping as 0, and I give some initial displacement to the structure, and P0 is 2000. Now we will compare our results with the analytical solution, and the natural frequency of the system with these parameters is equal to 7, and this is the analytical solution for a free vibration under the effect of the harmonic loading. As a starting case, I'm using a very large time step that's equal to 0.2, and damping is defined as equal to 0. Now let's see what will happen if I use a very large time step like this. I'm solving the same system with the implicit Newmark, explicit Newmark, and also the analytical solution, and this is the comparison of the results. So here the red line represents the results obtained with the implicit Newmark method, blue one is the explicit Newmark, and black is the exact analytical solution, and I'm plotting the variation of the displacement with respect to time. So as you can see, we see the results do not match. Of course we know, because we used a large time step. This also shows that the time step that we are using is not sufficient to obtain an accurate solution. So again, looking at this complicated time history result, even for a single degree of freedom case, doesn't tell us much. So let's again plot the response in the frequency domain and check. Now what we see here is, now the natural frequency of the system is equal to 7, so we see a peak at frequency equal to 7. The applied loading has a frequency equal to 2, so we see another peak here. Now we see something interesting here. Remember that we use a large time step for this problem, and when we look at the implicit results, the frequency is shifted, is decreased. Okay, the natural frequency, it affected the natural frequency of the system. Now we see a smaller natural frequency, and also the amplitude also decreased. Okay, this means that the natural vibration is somehow damped in the implicit Newmark algorithm with a large time step. And in the explicit approach, we see just the opposite. Now the natural frequency is larger according to this results, and the amplitude is also increased. So that's the main difference between the implicit, one of the differences between the implicit and the explicit results. Explicit algorithms tends to increase the natural frequency of your structure, whereas the implicit ones, they decrease it. But of course, we can always overcome such differences by using a smaller time step. So in that case, I'm using a time step that's equal to 0.01. So it means more computation, but more computation means an exact match. So the displacement histories are matched significantly. But remember that the velocities are the first derivatives of the displacement. So a small error in the displacement will be magnified in the velocities, and when you want to take a look at the acceleration, you see larger differences. But for this case, as I said, I use a smaller time step. Now let's take a look at the response in the frequency domain. So as you see, we have a perfect match in the frequency domain also. So yes, the implicit methods and the explicit methods have their differences, but they all converge to the exact solution as we decrease the time step.